Today we will learn about the ideal gas law. Our question of the day is what characteristics make a gas ideal instead of real? Let's say you have two equal volumes of different gases that are at the same temperature and pressure. They will have the same number of gas particles regardless of their identity due to Avogadro's law. Avogadro's law states that V1 over N1 equals V2 over N2, where V is volume and N is the number of moles of gas. Let's recall molar volume. We said that at standard temperature and pressure, 1 mole of gas is always 22.4 liters. Notice how each of these balloons has a different mass because they each have 1 mole of a different substance. Even though the balloons have different masses, they all hold 22.4 liters. So once again, the volume of a mole of gas at standard temperature and pressure is 22.4 liters. This means that if we know the volume of a mole of gas, we can plug that into the combined gas law and come up with the ideal gas law. Knowing 3 variables, you can determine the 4th using the gas constant. Don't worry about the derivation. You can do it if you would like, but we're just going to use the ideal gas law from now on. The ideal gas law is PV equals nRT, where P is the pressure in atmospheres, V is the volume in liters, N is the number of moles, R is a constant called the gas constant, which is 0.08206 liter atmospheres per mole Kelvin, and T is a temperature in Kelvin. Make sure you use the units listed here because otherwise they won't match the units of the gas constant. So the units won't cancel out and leave you what you're looking for. Now, try the show what you know questions, and when you are done, you can resume and check your answers. For problems number 1 through 3, let's use Avogadro's law. V1 over N1 equals V2 over N2. In problem 1, we have a 25.5 liter balloon holding 3.5 moles of carbon dioxide leaks. If we are able to determine that 1.9 moles of carbon dioxide escaped before the container could be sealed, what is the new volume of the container? Well, the initial volume was 25.5 liters and the initial number of moles was 3.5 moles. To get the final number of moles, we're going to need to subtract 3.5 minus 1.9 to get 1.6, since 1.9 moles escaped. Then we are going to solve for V2, so V2 equals V1 over N1 times N2, and when we type everything into the calculator, we will get a new volume of 11.7 liters. In problem 2, Jim adds 3.13 moles of argon to a 5.29 liter balloon that already contained 2.51 moles of argon. What is the volume of the balloon after the addition of the extra gas? Well, the initial volume was 5.29 liters. The initial number of moles is 2.51 moles. To get the final number of moles, we will need to add 3.13 and 2.51. This makes our new number of moles 5.64. We can then solve for the new volume by multiplying the initial volume 5.29 by the new number of moles 5.64 and dividing by the initial number of moles 2.51. Our new volume is 11.9 liters. Now let's look at number 3. A container with a movable piston, which means that the volume can change, currently holds 60.52 milliliters of gas and 0.38 moles of gas. The volume increases to 100.48 milliliters upon addition of a gas. How many moles of gas are now in the container? And how many moles of gas were added to the container? First, we'll set up Avogadro's law. To do this, we will need to solve for the final number of moles. Let's flip both the fractions over in order to get the number of moles on top, and then we can multiply both sides by the final volume, and we get the final number of moles is equal to the initial number of moles divided by the initial volume times the final volume. Let's plug in what we know. So our initial volume was 60.52 milliliters, our initial number of moles was 0.38 moles, and our final volume is 100.48 milliliters. Now let's type everything into the calculator. That will give us a new number of moles of 0.63. When we subtract 0.38 from 0.63, we get that 0.25 moles of gas were added to the container. Now let's look at problems 4 through 8. For these problems, we will use the ideal gas law, or PV equals nRT. A 2.50 liter container is filled with 4.38 moles of argon. If the temperature is 225 Kelvin, what is the pressure? Well, we are looking for the pressure, so we want to solve the ideal gas law for pressure. Let's rearrange the equation so that pressure is by itself. Then we have the pressure is equal to N times R times T divided by V. Our volume was 2.50 liters. Our number of moles was 4.38 moles, and our temperature was 225 Kelvin. Add to that R is a constant, the ideal gas constant, which is 0.08206 liter atmospheres per mole Kelvin. And we can actually plug in the information we've been given to solve for P. So we're going to multiply 4.38 moles times R, which is 0.08206 liter atmospheres per mole Kelvin, times the temperature, 225 Kelvin, and divide all of that by the volume, 2.50 liters. Typing this into our calculator, we get 32.3 atmospheres as our pressure. Now let's try number 5. The pressure of 3.2 total moles of non-reacting gases is 1.8 atm at standard temperature. What is the volume? First, we need to solve the ideal gas law, PV equals nRT, for volume, V. So we're going to divide both sides by P, and we get volume is equal to nRT over P. Our pressure P is 1.8 atm. Our number of moles N is 3.2. Our ideal gas constant is always the same, 0.08206 liter atmospheres per mole Kelvin, and standard temperature is 273 Kelvin. We can plug all this into our rearranged equation and get that the volume is 39.8 liters. Next, let's look at problem 6. The volume of a gas at standard temperature and pressure is 6.81 liters. How many moles of gas are present? Well, first we need to rearrange the ideal gas law, PV equals nRT, to solve for N, the number of moles. In this case, we're going to divide both sides by R and T. So we get N is equal to PV over RT. The standard pressure is 1 atmosphere, and the standard temperature is 273 Kelvin. Our volume is 6.81 liters, and the gas constant is always 0.08206 liter atmospheres per mole Kelvin. Plug all of this into your equation and you will get 0.30 moles of gas. Now let's look at number 7. What is the temperature of 4.0 grams of helium at standard pressure if the volume is 50.0 milliliters? Since we want to know our temperature, we will need to solve our ideal gas law for T. So PV equals nRT, we're going to divide both sides by N and R to get T is equal to PV over NR. Our pressure is standard pressure of 1 atm. Our volume is 50.0 milliliters, which is 0.05 liters. Then we are going to also plug in our ideal gas constant, which is 0.08206 liter atmospheres per mole Kelvin. And lastly, we need to find our number of moles. To do this, we must convert 4 grams of helium to moles of helium using our molar mass. Since 1 mole of helium is 4.0 grams, then we have 1 mole of helium. Now we're going to plug all of these numbers into our ideal gas equation and type them in the calculator and see what we get. This means that our temperature is 0.61 Kelvin. Notice how, because our ideal gas constant has liters in it, we had to convert our volume from milliliters to liters. Always double check your units to make sure they match. Finally, let's look at number 8. What is the pressure of 70.9 grams of chlorine at standard temperature if the volume is 100.0 milliliters? Well, we're going to find pressure using the ideal gas equation, PV equals nRT. If we solve this equation for pressure, we get P is equal to nRT divided by V. So Rn is our number of moles, which we can find by converting 70.9 grams of chlorine to moles of chlorine. Then our R is going to be the ideal gas constant, which is 0.08206 liter atmospheres per mole Kelvin, always. Our T, or temperature, is standard, which is 273 Kelvin, and our volume is 100 milliliters. However, the ideal gas constant uses liters, so we must convert milliliters to liters by dividing by 1,000. We then have 0.1 liters as our volume. If we plug all of this into our rearranged equation, we can type this in the calculator and get our final result. The pressure is 224 atmospheres.